Nuclear astrophysics is a topic that many feel to be inaccessible, if not plainly ominous. While the formalities of the field may be exactly that, the surface can be thoroughly explored with minimal use of off-putting semantics. Abstractly, nuclear astrophysics aims to understand the origins of chemical elements as well as energy generation in stars. Nuclear astrophysics then, by extension, is the study of the evolution of the universe as a whole. Everything that is visible in the night sky is powered by nuclear reactions. Every planet, every environment, every city, and every life form is comprised of the elements that were slowly transmutated into existence over the almost 14 billion years that the universe has so far endured. The explanation for the origin of the elements is expressed in the so-called theory of nucleosynthesis, which currently contains accepted postulates for the formation of every element ranging from hydrogen to uranium. This theory is constantly being improved by scientists who aim to explore such questions as how did the universe create the elements, what can astrophysical events tell us about the fundamental properties of matter, and how is the energy that powers the stars and astronomical events created. One man who has made it his life work to answer some of these questions is Dr. Art Champagne, a William C. Friday Professor of Physics and prior department chair at the University of North Carolina at Chapel Hill, who specializes in nuclear astrophysics. Dr. Champagne examines methods used to improve the study of the field, primarily at the Triangle University's Nuclear Laboratory, or TUNNEL for short. TUNNEL is operated by Duke University, the University of North Carolina at Chapel Hill, and North Carolina State University, and is located in Durham, North Carolina. The TUNNEL operates 3 sub-facilities, the first 2 being the Tandem Accelerator Laboratory, known as TAL, and the Laboratory for Experimental Nuclear Astrophysics, known as LENA, both of which are known as low-energy charged beam accelerators. The third and final facility is the high-intensity gamma-ray source, known as the Higgs, which happens to be capable of producing the highest intensity polarized gamma-ray beams in the world. Due to his outstanding work within the field of nuclear astrophysics, Dr. Champagne was appointed to become the 6th director of TUNNEL in 2016. The main problem facing scientists within this field is the extreme circumstances, methods, and equipment needed to simply reenact the reactions that are happening all over the universe, surrounding us at all times, which are unfortunately very impractical to study as they are, for the most part, many, many light years away. Solutions to this issue have been found in 2 major ways, the first being computational modeling of astrophysical events. This, namely for the lack of physical equipment needed, is often the most cost-effective and therefore most common method through which research is conducted. However, empirical evidence is still required for a theory to be generally accepted by the greater scientific community, which leads us to the second solution, particle accelerators. These are massive machines that employ electromagnetic fields to accelerate particles to near light speed in the form of well-defined beams that then collide into targets or other beams. The most famous of these accelerators is known as CERN. However, there are many spread across the Earth, including the aforementioned TUNNEL. Dr. Champagne and his fellow astrophysicists share a main goal that is to progress the technology behind the accelerators, as well as the accuracy of computer models. This has led to many discoveries which he has published in his complicated works containing such hellacious titles as Statistical Methods for Thermonuclear Reaction Rates and Nuclear Synthesis Simulations, Ratio of Germanium Detector Peak Efficiencies at Photon Energies of 4.4 and 11.7 mega-electron-volts Experiment versus Simulation, and Measuring the Neutrino Lumosity of the Sun with Lens and Mini-lens Prototypes. While these papers are obviously targeting fellow higher-level scientists, Dr. Champagne's work can in fact be simplified down to some much more comprehensible components. For the most part, he shoots particles of varying intensity that are radioactive at one another. This is known as beam-beam or beam-target fusion. And then he records and examines the results before applying them to the physical limitations of the known universe. The field of nuclear astrophysics has undoubtedly come a long way, but there is still one disturbingly major issue with it. It is yet to complete an elemental history of the universe, an endgame which comprises the very heart of the field. This research, as almost all research does, simply comes down to a human need to know. So long as scientists stay addicted to the innate satisfaction that comes with the quenching of curiosity, this seemingly endless goal may eventually be within their grasp. This is what makes this field so beautiful. It explores a question so vast and important that it is in many ways the ultimate enigma for humanity to crack. If the methods continue to improve and breakthroughs continue to be made every day, then slowly a picture of the universal history will be brought into focus, and humanity will finally understand its proper place within our universe.